All right, the next concept in thermochemistry is the heat required to cause a phase change. You should know that when something changes a state of matter, that heat is flowing into it or heat is being pulled away from it to cause the phase change. For example, in the last lecture, we talked about right now when we have a lake or a pond of water, okay, if the outside, so here's my lake with my water inside of it, if the surroundings, the air above it is cold, below freezing, the energy from the water starts to come out of the lake or pond, and that causes the water to change its temperature, to drop, to get colder. If there is a greater an amount of energy to be pulled strong enough that the temperature of the water drops below its freezing point, it's going to start to freeze. And if the air temperature is colder than its freezing point, it's going to keep pulling and drawing more and more heat from it, and that's going to cause more and more of the water to freeze. So it takes energy to cause phase changes. Either heat's coming in, and when energy comes in, we are thinking of things like melting or boiling. And then heat comes out when we're thinking of something freezing or condensing. Energy's got to come out in order for those phase changes to occur. Okay? Now there's a big misconception with phase changes, and that's, for example, the misconception is for water to undergo a phase change, it's breaking its bonds. Well, if that was the case, what would be happening is if the bonds were to break, the hydrogen-oxygen bonds would separate, and what we would get is we would get hydrogen gas and oxygen gas to form from that chemical reaction. We're breaking its bonds. But that is not what happens. You should know by now that when a state change occurs, we are still talking about water. It just is water in a different state of matter. So we're not breaking bonds. So when you have a pot of water on a stove and you take it off of the stove, immediately the water stops to boil, or very quickly it stops to boil. And that's because the energy stops coming into the water to continue its phase change. We have to heat the water up to its boiling point. That takes energy. But then to complete the phase change, we got to keep heating the water. And energy is needed to complete the phase change. And that energy is not going into breaking the bonds, but instead something else. Does anybody have an idea of what it's going into? Where is the energy going to cause a phase change? And it's either going to break or vice versa to make not a bond, but an IMF, intermolecular forces, the sticky forces of attraction that holds molecules together. If we're going to break those sticky forces, if you have water that's in liquid state, it's attracted to all the other molecules in the water. For it to break away and enter the gas phase as an independent particle away from all of its other liquid particles, it must have enough energy to break away from those intermolecular forces that's holding it in the liquid phase. So the energy is not going into separating the water into its elements, but it's going into breaking the intermolecular forces, holding it in the liquid state. Vice versa, if we have a gaseous water, if I cool it enough, water vapor, we can start to make IMFs and cause the water molecules to cling to each other, and now the liquid is condensing. So, heat coming in to melt or boil something is going to have a positive Q. Energy's coming in to make those intermolecular forces. To break. When energy's coming in, energy going in to break those intermolecular forces. If we are going to freeze or condense something, we're going to pull energy out, and that's because we are making intermolecular forces, and energy's got to be pulled out to do such. Okay? So that's what's going on conceptually, is it has to do with the intermolecular forces that holds the particles or the molecules together between the substances. We're not breaking the chemical bonds. If we're breaking chemical bonds, that's chemical reactivity. It's not a state change. Now, whenever we do state changes, we tend to get this graph, which is called a temperature time graph. And if you start with a substance, which A is, in its solid phase, and this is an example of a heating curve, temperature, energy is going in at all times. Energy is going in to do A to B and B to C, so on and so forth. When we get to F, it is a gas at a specific temperature. Now, the temperatures at which we have the two flat sections, the flat sections are the phase changes, where we're going from a solid to a liquid in BC. So BC is the solid to liquid phase change, and that's the amount of energy it takes to complete this phase change, which in this case is the energy it takes to melt. You'll notice that the temperature does not change, and that's because the energy is not going into making the molecules move faster to increase their temperature. The energy is going in to, in this case, to break the intermolecular forces. Okay? The particles that make something solid, the particles, all they can do is vibrate. They can't move past one another. But once we get to the phase change BC, we give the material enough energy that the molecules or the element can begin to slide past one another, and now the material has more freedom of movement. It's becoming a liquid. So energy's coming in. The equation for that, and again, we're solving for Q, which is heat, thermal energy. The amount of thermal energy it takes to complete the phase change is given by mass times HF. HF is called the heat of fusion, and it is a constant dependent upon what the material is. And it's really based on the amount of IMFs the material has. The more IMFs it has, the higher its heat of fusion is. So to calculate the amount of energy it takes, now this is the amount of energy it takes just to complete the phase change. It is not the amount of energy it takes to get it to its boiling point. Once we get water to its boiling point, how much energy does it take to complete the phase change? To make water, in this case, if this is water, how much energy does it take to get ice, which is at 0 degrees, to become C, which would be water at 0 degrees? When we have ice water that's melting, if you were to stick a thermometer to ice water, it would register 0 degrees. It stays 0 degrees until all of the ice has melted. And so the temperature is constant until the phase change is complete. And so during the phase change, there is no temperature change, and that's symbolized by the equation. Okay? DE is exactly the same thing. It too is a phase change, but now we're looking at a liquid going to a gas. And this is, again, going to be causing it to become we're looking at its boiling point. And again, energy's coming in. And again, now we're going to break more IMFs. Now we go from molecules that are held together by those IMFs in the liquid phase. They break away as independent gas particles, which have much more freedom of movement, and they enter into the gaseous phase. That too is given by a very similar equation, but it's given as mHV, the mass, how much material do I have, times HV, which is the heat of vaporization. This is the amount of energy it takes to complete the phase change. So once your pot of water begins to boil, how much energy would it take to have all of that water go from water at 100 degrees, which is what is it at D? Here we have water at 100 degrees, to becoming all vapor, all gas at 100 degrees. How long would it take for that pot of boiling water to totally vaporize and have no water left in the container on the stove? Okay? The other sections, A to B, this is where the ice is heating up. And what's happening here, conceptually, is the molecules are moving faster. Now, as a solid, the molecules can only vibrate. They can only wiggle because they're locked together by very strong intermolecular forces. But as I warm the ice up, the molecules begin to vibrate faster and faster and faster. Eventually, they vibrate so fast that they can break the intermolecular forces holding them together, and now the material begins to melt. Because we do have a change in temperature, the equation we can use for that is mc delta T, the equation we had from the last lecture. So when we have a change in temperature, you are always going to use mc delta T, depending upon what the material is. And not only what material is, but what state it is. Okay? C, here we're going to heat the water up. So if you can think of the molecules buzzing around and moving, they move faster and faster and faster until they begin to boil. And again, that's given by mc delta T. And lastly, once the vapor is completely evaporated into a gas, we can heat steam up even further. And we can heat that steam up, causing its temperature to go up even further. Therefore, we have a maximum temperature which liquid can boil at. Water can boil at a certain temperature, and usually that maxes out when we expose it to atmospheric conditions. But steam, gaseous water, we theoretically could heat up to enormous temperatures. Okay? So these are the equations that we're going to utilize to either change the material's temperature, Q equals mc delta T, or we have these two new equations that we can use to complete the phase changes. Okay? A couple of the conceptual concepts, look at this graph before we move on to the math problems, is question 1 down here. It says the slopes of the ascending sections are not the same. What does this tell us about the material? Any thoughts on that? Well, the concept of that tells us that the substances have a steeper slope. That means they are able to heat up more quickly. Well, what would cause something to heat up more quickly? That, again, has to deal with the specific heat. Specific heats of materials change with what state it is. So a specific heat of a material is state dependent. When they're in different states of matter, they heat up differently. So something that has a steeper slope means that it has a lower specific heat. And something that has a higher specific heat will have a shallower slope because it doesn't heat up quite as quickly. All right, so one thing to note is on the national exam, I've not really ever seen them do that to students where they have to worry about the specific heat changing with the material. Usually they'll give you just one specific heat for water, and you'll just use the same thing regardless if it's ice or steam or water. But just understand that the steeper the slope is, the quicker the material is heating up, and that usually has a connection to the specific heat. The steeper the slope, the smaller the lower the specific heat value. The lower the specific heat, which means the smaller the specific heat, it takes less energy to heat up that material. Okay? So that's a nice little thing to kind of remember. The shallower the slope, the slower the slope rises, the greater its specific heat. So it's actually an indirect relationship. Okay? The shallower the slope, the greater its specific heat because it takes more time and therefore more energy to heat that material up. One other concept on here is something that I see more often asked, and that's the section of DE is much longer than BC. What does that tell us? It takes more time to boil something completely than it does to melt. And if we assume that the heat is being absorbed at a constant rate, what that indicates to us is it takes a lot more energy to boil something completely than it does to melt something. And that's because the intermolecular forces to cause a liquid to become a gas, there's a lot stronger intermolecular forces to make that break than it does to go from a solid to a liquid. We break much more intermolecular forces to form gaseous water than it does to make liquid water, because we physically remove that particle from all of the other particles in which it is attracted to. So it takes much more energy to boil something than it does to melt something. So the HV constant is always much, much bigger than the HF constant for a material. That's what it tells us. It takes more energy to boil something than it does to melt it. All right, let's turn to the math. Because what might be a good thing to do is to go back to a graph and identify where am I starting, where am I stopping. In this problem, I have ice already at 0 degrees. All I want to do is make it become water at 0 degrees. I'm just completely... All right, so problem number 1. How much heat is needed to melt 100 grams of ice that is already at 0 degrees? So all we are doing is completing the phase change. Students really struggle in these problems, phase change. To do that, you have to know what the HF is for water. Because we're melting it, we're looking at the HF value. HF is used whenever we are melting something or we are freezing something. We use HV whenever we are boiling something or we are condensing something. Okay, so the HF or HV will always be given you to the problem. It wasn't given here, it's my apologies, but the HF would be for water, or is, 336 joules per gram. It takes 336 joules of energy just to melt 1 gram of water from ice to liquid. Okay, so because it's a state change, there is no change in temperature. We literally just have M times HV. All we have to do is multiply the mass of the sample by its constant. And that's it. So it takes 33,600 joules of energy to melt it. Now, would that be positive or would that be negative? We're melting it. Is that a positive value or a negative value? Because that's also very important in this unit. What makes it harder too is not only does the number have to be right, the sign has to be right. The answer is positive because, again, to melt something, it must absorb energy to break the IMF forces of attraction. Okay? All right, let's go do the next one. How much heat is needed to convert 85 grams of iron at 25 degrees to molten iron at its melting point? Now that's very important because if I think of a temperature time graph, I'm starting off at a temperature that's below the melting point. So if that first flat section is the melting point, I'm starting off at a temperature that is below its melting point, which means I've got the first step is I've got to heat up the iron and get it to its melting temperature. Is the temperature changing to do that? Hopefully you said yes. So since the temperature is changing, we are always then going to use MC delta T. Once we get it to its melting point, we have to further keep heating it to melt the material. And to do that, we are going to use M times HF. We've got to melt the material. So we have to add energy to get it to its melting point, and then we got to further heat it even further to completely melt the material. All of that takes energy, and to get the final answer to the problem, we have to just summate the final answer. Okay, so we have 85 grams of iron. The specific heat of iron from the last, or if you go back to the page 1 of the packet, it's 45 joules per gram degrees Celsius times the final temperature, which is 1538 minus 25. Okay, so if I take 1538 minus 85, I get a change in temperature of 1,453 times 0.45 times 85, and I'm going to call this one Q1. Q1 has an energy value of 55,600 joules. That's how much energy it takes just to simply heat the iron, just to get it to its melting point before we see the first signs of melting. The next step then is we got to melt it. Now it's solid iron at its melting temperature of 1538. We simply just got to melt it to liquid iron at 1538. To complete the phase change, we just multiply that by its HF, and before I showed this problem, I looked it up. The HF for iron is 247 kilojoules per gram. Okay, so 247 times 85, and I get a Q2 of of 20,995 joules. And my apologies, it was not kilojoules. I had to relook it up because I was like, that's a big number. It was actually 247 joules per gram. My fault. So multiplying 247 joules per gram times 85 grams gives me 20,995 joules of energy. Okay? So then all I got to simply do now is summate or add these two numbers together. And we get 76,595 joules. And if I want to round this number to three significant figures, it'd be 76,600 joules of energy would be needed in order to melt the iron, take the iron from solid, roughly room temperature iron all the way to molten iron. That's how much energy it would take just to melt 85 grams, which again, 85 grams is not really a large mass quantity, something you could easily hold in the palm of your hand. That takes a lot of energy to be able to complete that phase change. Okay? All right, let us see. How much heat is needed to melt ice, 10 grams of that is negative 10, to reach room temperature at 20 degrees. I always, in phase change problems, like to draw my little temperature time graph and figure out where I'm starting, where I'm going. So I'm at ice, which is solid, at negative 10. Am I at the melting point of water or am I below it? Negative 10 puts you below it. So I've got to go from, I'm going to change my color here. I've got to start here and I've got to get it to its melting point. Then I've got to melt it. Now, am I going to stop after I melt it? No, I then got to get it to room temperature, which is there. So I've got to go three sections of this phase change. I've got to first get the ice to get up to 0 degrees Celsius. Then I've got to melt it, and then I've got to get the water up to 20 degrees Celsius. So that requires three different sections of the phase change of the temperature time graph to be understood, so I need three different equations. Whenever I have a change in temperature, now does section A require a change in temperature? Yes, so I'm using MC delta T. Does the second step, the melting process, see a change in temperature? No, section B, we see the section is flat. We have to use M times HF. And then lastly, I've got to change the temperature and warm it up again. And again, because the temperature is changing, I'm using Q equals MC delta T. All right, so now this becomes, again, just simply a plug and chug. So step one, the mass is 10 grams. The specific heat of ice, we're going to assume to be the same as that of water, 4.18 joules per gram degrees Celsius. And I'm going to go from, I'm going to start at negative 10, but I'm going to go up to 0. So I'm going to do 0 minus negative 10. I'm going to increase temp 10 degrees Celsius. Multiplying, that gives me 480 joules. Takes 418 joules of energy just to get the ice to its melting point. Okay, Q2. Now I've got to melt it. The melting point, HF, of water is 336 joules per gram. Times 10, and I get 3,360 joules. 3,360 joules just to melt the ice into water. Now that's still water at 0 degrees. Now I got to warm the water up from 0 degrees to 20 degrees. So again, 10 grams. Specific heat is 4.18 for water. And now my final temperature is 20. minus 0, because I'm starting at 0, going up to 20, so I'm going up 20 degrees. So 4.18 times 10 times 20, and we get 836 more joules of energy. Okay? So then, altogether, if I look at this problem and summate it all up, 418 plus 3,360 plus 836, we get a total amount of energy of 4,610 joules, rounding to 3 sig figs. All right, so that's how you do these problems. And again, the best thing to do is to draw a temperature time graph and try to see where am I starting, where am I stopping. If it's an ascending section, I'm going to use Q equals MC delta T. If it's a phase change, the two flat sections, you might only do one of the flat sections. You might only melt the material. Maybe you're just boiling the material. You have to figure out how many phase changes have occurred and then add it all together once you get all those values. All right, down below, letter D here, D and E. This is an example problem from an actual AP question from the national exam. I'd like you to read through this and see if you could do problems D and E. And then I'm going to stop the lecture myself and do the math. And when I pop this lecture back up, you're going to see the completed answers to D and E. But please pause the lecture now. See if you can try to do the problems on a free piece of paper, and then start the lecture up again and see if you can get these two problems right. Again, these are actual released test questions. All right, so here you can see the answers to this problem. Now, they threw you a little bit of a curveball, and I was trying to see if you could pick up on it because, again, students really struggle with units. It gave me these quantities in moles, but they gave me, instead of mass, they gave me moles. And they gave me moles in all of both the specific heat, but also the heat of fusion. So you're so used to doing Q equals MC delta T when the specific heat is given per gram. But if it is per mole, I can just simply then multiply the moles by the heat, the specific heat in a mole quantity. And again, what will happen then, if I turn my color again, the moles will cancel. And I can keep the temperatures in Kelvin because a degree change in Kelvin is the same as a Celsius. The kelvins will cancel, the moles will cancel, and we get 15,000 joules of energy just to get aluminum up to its melting point. Okay? Then to complete the phase change, they gave me again 1 mole, and they did give me kilojoules per mole. So I multiply them, the moles cancel, and I'm left with kilojoules. But here's the thing that students often don't put units into the mathematical problems, and they don't understand and realize that the top one is in joules, the bottom one is in kilojoules. So we have to convert the kilojoules into joules, and we do that by multiplying by 1,000. And doing so, we now get both of the quantities in joules, and we can add it up. So there's lots of little things here that students screw up on if they don't look at units. It's so critical to look at units and understand how the equations work themselves out. So it takes 25,900 joules of energy to melt aluminum, which is roughly at about 25 degrees Celsius, 1 mole of it. So that's about 27 grams, all the way to melt it. Now, in E, this is something we haven't quite gotten to yet, but this right here tells me the energy in kilojoules per mole. Well, you'll notice that the reaction that this reaction produces this much heat for 4 moles of production. So we have to first divide this by 4 to get it per mole. So dividing by 4, I get 837 kilojoules per mole of aluminum. To get and extract aluminum metal from its ore. Well, again, that's kilojoules per mole, so I need to multiply by 1,000, and I get 837,000 joules of energy to extract 1 mole of aluminum from its ore. Well, what takes less energy? The energy to recycle it or the energy to extract it from its ore? And we can see that 25,900 is much, much smaller than 837,000. So it takes much less energy to recycle something like aluminum than it does to get it from mining it from the ground. And this is why aluminum is one of the things, and most metals, why it is such a convenient thing to recycle is because, energy speaking, it is convenient and also more affordable to recycle something than it is to get it from mining it and producing it from the ground. Things like plastics, not so much. Plastics is much cheaper to just simply create them than it is to recycle them, and that's why you see we're having that big issue with so much plastics being around the world in our waters, polluting our environments, is because it's cheaper to just keep producing more plastic than it is actually to recycle it. And if it was cheaper to recycle plastic, we wouldn't have the type of big issues we're having with keeping the environment clean with plastic bottles and so on and so forth. So do your part. Try to minimize the amount of plastic you use. It'll make the world definitely a better place until we can figure out processes to make recycling plastic much more convenient. Okay? Again, this is how you do heat of fusion and heat of vaporization problems. If you have any questions, please get a hold of me.